let's prove the following lemma. So consider all the left cosets. Okay, so what is a left coset? So we need to remember, so we've defined cosets, right? We define the coset AH equal to AH, right? The set of all A times little h, where little h is a member of big H, meaning it's just A times any member of the subgroup here, right? So G is a group, H inside G is a subgroup, and so we call this a left coset because A is sort of being multiplied on the left here. It is being multiplied on the left. So we could just as easily define HA, a right coset, to be little h times A, for H in H. And so when we're talking about the left cosets and the right cosets, and so the point is that the reason I'd say left here is because the multiplication in the group might not be commutative. If it's an abelian group, these two are definitely the same thing. But if it's not, we don't necessarily know that. So what we have two different notions of coset. But okay, this is a little bit of a minor detail, and right now we don't care too much. So let's consider all the left cosets. And we've already proved that these partition the group G. And now we want to show that all these left cosets have the same order. In particular, this order is, the order of the set 1H is the same. The size, the number of elements in the set 1 times H is, of course, this is just the subgroup H. So in particular, we know what that same order is. It's just the number of elements in H. So they all have the same order, they all have the same number of elements, and that number of elements is exactly the number of elements that are in the subgroup H. What's the proof? Well, let's take of sets. Maybe I'll call it F, from H to AH. So, I guess maybe I should say, pick an arbitrary element A in G, and then we are going to show that the size of AH is the same as the order of the subgroup H. And that will tell us, in particular, this and this, right? It'll tell you, it'll tell you what the size is. So, and what I'm going to do is I'm going to define this map right here, and it's going to take any element of H, and we're going to map to AH. And I want to show that this map is a bijection. So how can I show that this map is a bijection? Well, there's two ways. One is to show that it's injective and surjective. The other one is to find an inverse map. So let's find an inverse map. F inverse, and F inverse will go from AH to H, and it'll just take some element right back to H. This is multiplication by A inverse, right? You know, A inverse, maybe I can write it like this. AH goes to A inverse times A times H, which is just H. And so if I compose these maps, F after F inverse, well, if I first apply F inverse, that'll be A inverse times A times whatever I have in here. Whatever I have in here, A inverse A times G, which is G, so F after F inverse is the identity, and likewise F inverse after F will be, A inverse A, which would be G. And, as long as, as long as this map is, as long as this map, these compositions are the identity, we know that both of these maps are then going to be injective and surjective. And so this map is a bijection. And in particular, when you have a bijection of sets, they have the same number of elements. So we've proved the theorem. A little check there because we've proved the theorem. So now that we've proved this theorem, we can define the index and so the way it works is you have the big group G and then the subgroup H, and then we write it like this with the sort of brackets like this. So the index and you read this as the index of H in G. So the index of H in G is defined to be, so index, because this is a definition, is the number of, say, left cosets. And so in particular, based on our theorem, since they all have the same order, we can write down that, we have the order of the group H, and then the number of them. And since these form a partition of G, that will be exactly the same number of elements as the number of elements in G, which is the order of G. So maybe this is kind of important. This kind of deserves a box around it, and I'll call it a corollary. And so this is called the counting formula. So the counting formula says, and we just proved it, and the thing we used the most was, we're talking about left cosets and showing that the orders are the same, and then we used the fact that in the definition of cosets that equivalence relations form a partition, right? So using the fact that this is a partition and the fact that all of these are the same, we just count the number of them and write this equation down. And so the counting formula is something that in future videos we will use to prove theorems about groups.